Hello everyone, and welcome back to this series on financial mathematics. Today we're going to be continuing our exploration of some very important topics, in particular variable interest rates. So what exactly is a variable interest rate? Up to this point, we've been assuming that we're able to jump from time t is equal to 0 to 1 with some factor alpha, from 1 to 2 with alpha, from 2 to 3 with alpha, and so on. In particular, for each of these jumps, this alpha has always remained the same. In particular, alpha was always equal to 1 plus this effective interest rate I. So in particular, if we want to go from 0 to 1, we can represent that as alpha 1, and then from 1 to 2 is alpha 2, from 2 to 3 is alpha 3, from 3 to alpha 4, and so on. So from n minus 1 to n, we can represent that as alpha n. So generally speaking, alpha k can be represented as 1 plus ik. So notice for the general case where we usually say that these interest rates are fixed interest rates, then what exactly does this mean? This means that I1 equals I2 equals I3 and so on for all time t, right? So that's what we usually refer to as fixed interest rates. But usually, interest rates change throughout time because people's overall view of money and also time changes as well, right? Inflation, for example. So under the typical fixed interest rate, if we define u to be equal to 1 divided by 1 plus I, or 1 divided by alpha, then if we have a sequence of cash flows, let's assume that the sequence is represented by C1, C2, all the way down to Cn. So let's assume that this is an annuity, not a perpetuity. Then the present value of this sequence of cash flows can be represented as the sum from k is equal to 1 to n of the cash flow value ck times nu to the power of k, right? And we have used this formula in so many ways up to this point in time. So generally speaking, we can also represent this as the sum from k is equal to 1 to n of ck divided by 1 plus I to the power of k as well. So what we're now going to do is we're going to change this I to change with time as well. So how would you be able to generalize this? So generally, the present value of a sequence of cash flows can be represented as the sum from k is equal to 1 to m of ck divided by 1 plus ik raised to the power of k. Okay, so that is exactly what we're actually going to be looking at today in a little bit more of a detail. So let's just look at a quick example. So let's assume that our I is equal to 3.8, and let's assume that this is a fixed percentage interest rate, right? So if we let, for example, CK be equal to $3 for all values k from 1 to all the way down to, let's say, 50, then what is the present value of the sequence of cash flows? Well, that's obviously going to be equal to 3 times the present value of a unit annuity, where n is equal to 50, right? And I is equal to 0.038. So that's going to be equal to what? So that's going to be equal to 3 times the sum from k is equal to 1 to 50 of 3 divided by 1 plus 0.038 to the power of k. Now, keep in mind, we do have a special formula for this. In particular, that's going to be 3 divided by I times 1 minus nu to the power of n, where nu is the reciprocal of alpha, or 1 over 1 plus 0.038, and n is equal to 50 and I is equal to our 0.038. But generally speaking, if our I changes, then this formula is not really going to be much useful for us if the interest rate is indeed variable. So if you want to work with arbitrary cash flows and arbitrary interest rates that need not be fixed, then this representation obviously is going to be a little bit more useful for you. But for this particular case, you should be able to find that the present value of the sequence of cash flows of size 3 from 1 to 50 is just going to be equal to approximately $66.72, right? And keep in mind, this is with fixed effective interest rate I, right? In particular, what do we mean by fixed interest rate I? That means IT is equal to 0.038 for all t. Right? So now let us see if we can use these principles and make the interest rate variable and see if we can find the present value of the sequence of cash flows under that. So now let us assume that we actually know how interest is going to change in the future. Unrealistic, but let's assume just for the sake of this example. So let's assume that IT is going to be equal to 0.038. So this is the same effective interest rate as we had before, but now let's assume that it changes with respect to time. So let's add some more fun stuff to it. So let's assume that this is 0.01 times the sine, so this is the sine cosine sine, of 0.51 pi times t. All right, so here we have a representation that gives you the interest rate I at any time t for which you desire, right? So this, since it's a sine curve, this means that the interest rate follows a periodic pattern, okay? So this is what we call a periodic interest rate, so a periodic interest rate. So if the interest rate is equal to something today, eventually it will be equal to the same exact interest rate, and then another time later it will be the same, and so on. So how do we interpret this in case you do not remember all of the things about sine and cosine? So when you have a constant here, so this is just a constant c, let's say, and then you have just a basic sine function where t is raised to the power of 1, and this is another constant, again, let's call that another c. Then we interpret this c in front is the on average, the interest rate is equal to 0.038, right? So that's going to be the middle of your sine wave. So if we look at this from a graphical perspective, so here's going to be our 0. So our 0.038 is going to be this dotted line right here. Right? And then the sine wave, since this coefficient is positive, what we're actually going to see is it's going to go up, and then it's going to go down, and then it's going to go up, and then it's going to go down, and so on. Okay? So this constant in front of the sine wave, some people usually refer to this as the amplitude of the sine wave. This will tell you the range of this sine wave. So let's see if you remember how to interpret this. So the range of sine, in this particular case, by default it's from -1 to 1, but we have shifted up. But the range is usually equal to 2, one above and one below the horizontal axis of symmetry. So on average it's equal to 0.038, and it's going to be plus or minus this number in front, so 0.01. So that's going to be the range of this particular sine wave. So if we just evaluate this little simple value, then the range is going to be equal to, and this is going to be inclusive, 0.028 up to 0.048. So if we include this information into this picture, so let's draw a couple more horizontal lines representing the maximum and minimum values that it obtains. So this is going to be equal to 0.048, and this is going to be 0.028. All right? Now the next number that we're going to be looking at is going to be the number inside of sine, right? And that's going to be this number right here next to t. And this is going to tell you how often this sine wave repeats. So in case you do not remember, the period of this sine wave is going to be 2 pi divided by this number, right? So 0.51 pi. So generally, in case you don't remember, if you have y is equal to sine of kt, then its period, how often it repeats, is going to be 2 pi divided by k. Right? So therefore, if we have y is equal to the sine of 0.51 pi t, that's a 5. Doesn't look like it, but it is indeed a 5. So 1 pi t, then the period will be equal to 2 pi divided by that number, 0.051 pi. Right? And once you actually work that out, that's going to be approximately 3.92. And let's assume that the time t, let's assume that this is t, is in months, so this is also going to be in months as well. All right. So if we want to go up and add more details to this curve, so this point is when the curve starts to repeat. So if we call this time t is equal to 0, then this is going to be 3.92 months later. And if we keep on going all the way over here, so that's 2 revolutions of this curve, that's obviously going to be equal to 3.92. So 3.92 times 2, that's going to be equal to 7.9, almost 8 months later. And if you want to figure out what that number is, or potentially that number, well, that's obviously going to be half of the period. So that's going to be equal to 1.96. And if we go up another 1.96 from our 3.92, that's going to give us approximately 5.84. And if you want to find what that maximum value is located, that's obviously going to be half of 1.96. And if you want to know where this minimum interest rate occurs the first time, that's going to be the average of 1.96 and 3.92 approximately. Okay? So that gives you a sense of what's going on with this interest rate. How often does this interest rate repeat? When does it reach its maximum interest rate? When does it reach its minimum interest rate? And so on. All right. So if this is the case, how do we find this particular structure? Okay. So the present value for this is going to be equal to, keep in mind, generally speaking, it's going to be the sum from k is equal to 1 to, let's say, again, 50, so we can compare to the other number, which was 66.72. And let's assume that that sequence of cash flows was still 3. So it's going to be 1 plus ik raised to the power of k. So when you use that particular function, it, and of course make sure your calculator is set in radians, you can find that this is approximately equal to $67.66 for this, right? And keep in mind, for this, there's typically no nice formula to evaluate this, so you have to actually use that function or summation notation in your calculator or software in order to get this particular number. Right? So of course, if the function is not very nice, there's not much nice math to evaluate, right? But we do have our software to help us when things become a little bit more realistic. Okay? So that's if we have our periodic inflation rates, but notice that on average it does stay constant, right? But technically speaking, it doesn't have to stay on average constant. It can actually change quite a bit. So let's again assume, as another example, that we have it is equal to 0.038, and let's actually put a t in front of this, and let's have the same other periodic form, 0.01 times the sine of 0.51 pi times t. So what would this look like in the graphical sense? So again, we're going to have an initial value of 0.038, but notice that this is practically a constant between 0 and 1, and this is a linear function. So instead of staying flat, now what we're going to have is we're going to have a line that's going to be positive sloped, the slope being 0.038. And what you're actually going to have is you're going to have your interest rate sort of oscillate in an upwards trend. So that means we can say that on average, the interest rate is equal to 0.038 t, right? So the longer you go in time, the higher the interest rate is going to be, right? So this is obviously your long-term inflation with no hope of it ever going down, right? So with this, obviously, you can find the present value in the similar way before, but I'll leave this as a calculation exercise for you and to see if you can see, or maybe you can even guess. Do you think this is going to be higher than the 67.66 and the 66.72 values for constant interest rates and the periodic interest rates, or do you think it's going to be lower than those, right? So leave in the comments what you think with that, right? But this is the general structure of what we have, but it assumes that you have to know what this particular pattern is. But what if we don't? So now comes the important question. If we typically do not know the interest rate for time t is equal to 0, and this is obviously because it hasn't happened yet, how are we going to solve for it? How are we going to calculate present value if we don't know the interest rates of the future? Right? So we do have information about the interest rate in the past though, right? So if this is t is equal to 0, and obviously this is going to correspond to the past observations. So here's our past observational data. Then what are we actually going to have, right? So here's our vertical axis, and here is our t-axis. So let's assume that the interest rates, kind of went up, and then they kind of went down, and then they kind of went up, and then they kind of went down again, and here is the interest rate for today. So how are we going to figure out what the interest rate in the future is? Well, one can say, okay, well maybe I can fit a curve or some maybe polynomial or something, and then extrapolate it out into the future, right? And who knows what that function is that we fit on the left-hand side, but nonetheless, this gives us predicted values of interest. So this obviously is going to give us predicted values, which I'm going to represent by I hat of t. So these are predicted values for t greater than 0, right? So this is predicted it values, right? So is it possible that the interest rates are equal to this? Yes. Is it possible that they're not? Of course as well. All right, so we can always fit curves or approximations on the left-hand side, but keep in mind the closer you are to the data that you have predicting, the more trustworthy it is, right? So local approximations to things we know are typically more trustworthy, right? So the farther you out, obviously, the more the lack of confidence increases as you get farther and farther away from the support of your prediction model, right? So overall, the ability to create such approximations of curves is, of course, a deep, deep field. Some people usually refer to this as time series analysis, or time series regression, or time series approximation. That is, you're trying to model something with respect to time t. Now, for the goal or for the conversation of this particular discussion, we're going to assume that this time series regression model is provided to you. So whatever this green thing is that we've graphed on this curve, this is the best thing that we can get based upon the data for which we have. Right? So obviously that's a very difficult topic, right? But let's assume that, if we have an approximation I hat of t, then we can use it just like we did with the previous examples, right? But keep in mind, we're kind of just looking at it with respect to time, and technically nothing depends on time. It depends on other things that we observe through time. So how can we maybe do a more practical way without having to do any serious math? All right, so sometimes predicting I with respect to only time is very difficult. So what does interest rate depend on? Maybe we can observe interest rate with respect to time and another variables. So what does interest rate depend on? Well, it probably depends on several different things, but one of them is usually economic conditions. Economic conditions. Some people might not call it conditions. Some people might call it economic classifications or economic classifiers. So if the economy is doing well or the economy is doing bad, maybe you can approximate the interest rate a little bit better with that newly found information. So there's several different ways to classify the state of an economy, GDP being one of the variables, and there's several different classifiers that you could attach to the economy as well. I'm going to give you 5 basic ones, but I'm not going to formally define them. That's not really the goal of today. So let's assume that we have an economic classifier of deflation. And then we have recession. Usually these two are viewed as bad things in the general sense, but there are some counterexamples to that perspective. And then we have stagnation. Then we have economic growth. And then we have economic inflation. So typically speaking, when you look at the interest rates under these particular economic conditions, and let's assume that this is IDIR, IS, IG, and II, for example, and let's assume that they, of course, change with respect to time, even within their associated economic states. These are typically ranked against each other. So typically, they follow, and when I say typically, I mean not always, the inequality above. And you're like, I didn't draw an inequality. Of course I haven't. So usually this is less than this is less than this is less than this, right? So usually in inflation, interest rates are higher. Usually in deflation, interest rates are lower. And there's many economic reasons of why that sometimes is, but we're not going to get into it today. So how can we use this to our advantage? So first off, let's assume that the economy cannot be in more than one of these states at a time. So therefore, these events, deflation, recession, stagnation, growth, and inflation, these are mutually exclusive. Let's assume at least, right? So this is mutually exclusive events, and let's assume that they are the only classifications, right? So if I take the probability of being in one of these states and add them together, I should get 1. So these economic states pretty much partition the probability space associated to economic condition. So how exactly would you use this to approximate interest rates? So let me sort of give you a strategy that most people will be able to follow. So for each time the economy is in, let's say, deflation. So for each time the economy is in deflation, keep track of the interest rate at that particular time. So for example, you're going to have ID1, ID2, ID4, ID7, ID8, and so on. So these are all of the times for which it was in deflation, and let's assume that we observe the interest rates during deflation. So what you can do for these particular numbers is you can calculate the average interest rate during deflation, right? So you add them all up and divide by how many you observed, right? So once you have that, you can do the others. So similar for, let's call them IR bar, IS bar, IG bar, and II bar, right? So these are the average interest rates while the economy was in each of those rates, right? So keep in mind there's actually a couple different ways to calculate averages here. So one of them is the arithmetic mean, which is usually represented by x bar. So x bar usually is going to be equal to the sum of each of your values, and then divided by how many you have. And then we have another metric, which is usually called the geometric mean, and that's usually abbreviated by G bar, and this is going to be the nth root of the product of each of your values, xk. So you multiply by all of your values, usually they're all positive, and then take the nth root of that product. Usually when we're dealing with interest rates and things that increase geometrically or exponentially, most of the time G bar is more appropriate. So let's actually write that down. This is typically more appropriate. That is, it gives you more interpretable results of what's actually going on for things that change via percentages. Okay, but some people do use that arithmetic mean, but geometric mean typically is more useful when analyzing interest rate changes, right? So now we can estimate the interest rate or the average interest rate via either arithmetic or geometric means in each of these economic conditions, right? So what else can we do? Also estimate the percentage of time the economy was in each of those states, right? Because we have, for example, 500 observations. Some of them were in depression, some of them were in recession, some of them were in stagnation, some of them were in growth, and some were in inflation, right? So calculate the percentage of your observations, and obviously this has to range a good amount of time, and then you can approximate, for example, assuming that each event is independent. It's a strong assumption, but one can make that, at least for the start, that at a randomly selected time, what's the probability that the economy will be in recession. So once you have these percentages, then we have approximations for the probability that a randomly selected time we're going to be in depression, the probability that we're going to be in recession, the probability that we're going to be in stagnation, the probability that we're going to be in growth, and the probability that we're going to be in inflation, right? So these are approximations of probabilities, and keep in mind each of these must be between, potentially inclusively, from 0 to 1. So once you have this, then you can build a nice little summary table, which I'm going to pause the video and then write this out and show you what you could get after this analysis. So once you've done all those calculations for your data set of observations, for which you've kept track of all of your interest rates, all of your economic states, you've calculated the estimation of the probability that you're going to be in any of these states, assuming independence, again, a non-practical assumption, but it's good for the start. And also we're going to be approximating these interest rates, not the interest rates directly, but the average interest rate during depression. Because obviously, when you're in depression, the economic state that is, yes, it's not going to be fixed throughout all of depression. It will fluctuate throughout depression, throughout recession. Obviously, it's not going to be fixed. It will fluctuate. So we're approximating the average interest rate in each of these economic states, right? So here, notice I'm doing probability hat. These are estimations of probabilities. And this is interest rate. That is interest rate bar hat. So it's an estimate of the average of the interest rates in each of these categories. So we, if we look at this particular thing, we see, okay, depression, recession, stagnation, growth, and inflation. As we go from, I guess, the worst to the best type of economic state, let's say, not always true, but let's say, we can clearly see that the interest rates are increasing relatively monotonically as we transgress from one state to another. So obviously, when you are building this table, it's very important to note that when we sum up our p hat values in our table, you must get 1. This is a must for this particular thing, and it's also assumed that these are mutually exclusive events, and it's also assumed that these are all independent events as well, right? So mutually exclusive events, the sum of these proportions must be 1, and these are independent events, right? So one interest rate does not affect the other. Usually it's continuous, usually, but let's assume that that's not necessary, okay? So what are we going to have? So pick a random point in time, right? So for example, t, and t is typically going to be greater than or equal to 1. Okay, because we know what happens at time t is equal to 0, -1, -2, -3, and so on. So what we have here is that it is a random variable, right? Also, more importantly, the economic state also is a random variable, which I'll just abbreviate by RV. Right? So how can we find the expected value of this random variable? Right? So the expected value of I, in case you don't remember how to find expected value for probability mass functions, this is calculated by doing the sum of our interest rates times the probability of us having those particular interest rates I. Okay? So how would we find that? So from our particular data, this is going to be equal to, the first interest rate is 0.068. So 0.068. And what's the probability of being 0.068 on average? Well, that only occurs when we are in a depressive economic state, which has a probability of 0.06. And the next value is an interest rate of 0.072, which only occurs in recession. And the probability of recession is going to be 0.11. And this is going to continue all the way out to the last event, which is an average interest rate of 17.2%, and that only happens in our inflationary economic state, and that has a probability of 0.08. So we can clearly see that the expected value with that information is going to be approximately 0.11501, or approximately 11.5%. So, based upon the information that we have, the expected value of the interest rate at any random point in time without any new information is going to be somewhere around 11.5%. Is it possible that it's going to be more? Yes. Is it possible that it's going to be less? Of course. But on average, it is about 11.5% for all of our economic states, weighted with respect to the percentage of the time that those economic states occur. Now, obviously there is some variance associated to this expected value of interest rate. So finding the standard deviation of this random variable is also a necessary thing as well. So another metric, so again, this value is called the expected value. And then another metric, which is called the second moment, which is another way of measuring variance aside from standard deviation, is calculated as follows. So this is going to be EI squared. And instead of doing the sum of I pi, this is going to be the sum of I squared times pi. So how are you going to calculate this? So it's pretty much the same exact way. So it's going to be 0.068, the interest rate squared, times this probability value 0.06, and that's going to be added all the way down to 0.172 squared times 0.18. Notice that this is always going to have positive numbers in it, so it's always greater than or equal to 0. But for this particular data set, you should have a second moment of approximately 0.0144. Now, most people don't directly use this in their interpretation or analysis of things, but another metric, known as the variance of a random variable, can be calculated from the second moment and the mean, and usually it's going to be equal to the second moment of your random variable minus the mean of your random variable squared. So using that 0.11501 mean and this 0.0144 second moment, you can find that for our example, the variance is approximately equal to 0.0012. Now remember that the unit on expected value is the same as the unit of what we're doing the expected value of. So this is in percentages. But the expected value of I squared is going to be in squared percentages. So what exactly do you mean by a squared percentage? I don't know. But the same thing is going to occur for variance. So this is 0.0012 squared percentages. And you're like, I don't know how to interpret squared percentages. So how do you fix that? Well, obviously you take the square root of it. So this is called the standard deviation of I, which is always found by doing the square root of the variance of I. And keep in mind, variance is never going to be negative, so this is always going to exist. And for our particular data, let's change this color. This is going to be approximately equal to 0.0342, and this is now in percents. Okay. Now, I didn't look at the histogram of this particular probability distribution, so it's not as if we can assume that it's normally distributed or whatnot, but sometimes people usually only float around one or a fractional standard deviation from the mean. So if we build an interval, so interval with one standard deviation from the mean, then what are we going to have? So one standard deviation, which we usually abbreviate by 1 sigma. In case you don't already know, variance is sometimes abbreviated by sigma squared. Standard deviation is sometimes abbreviated by sigma. And the expected value of I is sometimes abbreviated by mu I. So we can subscript those with I as well, right? So mu for mean, sigma for standard deviation, sigma squared for variance. So one standard deviation interval from the mean is going to be what? So that's obviously going to be mu minus sigma and mu plus sigma. You could do mu plus 2 sigma and mu minus 2 sigma if you want 2 standard deviations. So using our 11.5% and our 0.03%, then you can find that a 1 standard deviation interval from the mean is approximately 8.08 to 14.92%. Right? So this gives us a 1 standard deviation interval that that you expect possibly the interest rate to be. So it's going to be somewhere between 8% and 4%, and then you can do whatever information you want. Obviously, if you do know the distribution, right? So suppose that the interest rates, is normally distributed, then what could we say about this particular interval? So this means that 68% of the time, I is in between 0.0808 and 0.1492. And if you don't know where this 68% comes from, this is coming from something called the empirical rule in statistics, which is associated to 1 standard deviations from the mean. And when I say normally distributed, I mean this little bell curve type of shape. And there's also a 2 sigma and a 3 sigma empirical rule calculation. And we usually say that's 68, 95, and 99.7% of the time. And you can find those intervals in similar ways, just like we did for the 1 standard deviation interval. Now, obviously, interest rates are continuous random variables, and we only were discretizing the interest rates based upon discrete economic conditions. You could perform expected values and standard deviations with continuous random variables. That obviously has to take us into the calculus realm if we desire to do that. But nonetheless, this is one way that you can use just simple math and discretization to help you analyze variable interest rates. I'm obviously avoiding some very super difficult and complex mathematical models to model variable interest rates because when predicting, there's always a hint of randomness. Sometimes we usually call that, like a stochastic system, whatever that means. And there's more sophisticated mathematics that go behind that, such as stochastic calculus and stochastic regression, which we will get into a long time later. Possibly not in this series, but more in a mathematical probability or stochastic probability series. But nonetheless, I hope this gives you some insight on how to interpret variable interest rates and how we can possibly approximate variable interest rates via regression, time series regression, and also how we can use statistics and probability models to help us model these complex objects. So I hope you enjoyed this video, and I'll see you in the next one. Take care. Thank you.